and the organizers to organize this workshop. So it's fun to participate. So thank you for the invitation. So it's really appreciated. So this is a good chance to talk about this rich hormone code. I've been working on it for a couple of years, 4 years or so. And normally I would just give a short talk. So normally it's 20 minutes talk, as you know it. And I didn't really have time to go much into the details. And recently when I started to work with people, collaborate, and with some students, and then I find that probably the topics and the papers, current papers in this research direction are not that accessible to the students who are new to the research problem. So this is the nice chance that I have quite some time to talk and to give the more details presentation of this research topic. So I suppose that a number of students here, and I think the recording of this and the slides of this, so after you go through all the slides and you have a sufficient knowledge to just jump right in the research of the problem of preparing rich Solomon codes. Okay, so my name is Hoang, and so I have a number of collaborators in this project. Olgisa Milenkovic and Iwan Rusmar are from University of Illinois, Urbana-Champaign. So when I was a postdoc and started this work, Hanmao Kia is an NTU and is my collaborator. Emanuela Viterbo is my postdoc supervisor at the time when I was at Monash, and Hien Chu she was a student at the time in Vietnam, and I believe now she's a PhD student, probably in Japan. And I also collaborated with Wei Chi Lee, Chiying Wang, and Hamid Shafakhani from UC Irvine. So currently I'm working with Đinh Thị Sinh from Thanh Nguyen University in Vietnam, and so Lakshmi Mohan is my postdoc currently working at RMIT, and I also work with Nhi Liu, so she's an intern. Okay, so the talk is about the problem of repairing rich hormone codes. So first I will motivate the problem, and then I will discuss the trace repair framework. That's the main framework that we use to study the repair problem of rich hormone codes. And then I will discuss 3 parameter regimes, and that discussion will include the codes currently used in industry, and I think there will be a lot of interesting questions there to discuss. And then along the way, I'll also give some open problems. So you guys can stop me at any time to ask questions, right? Because this is a long talk. So rich hormone codes have been used actually everywhere around us. And so they have been used in CD, DVD to protect the data from the scratches. If you see the QR code, it is everywhere. Then there's rich hormone codes behind it. If you use Dropbox, Google Drive, or Facebook, then all of these the storage systems, the cloud storage, they are using some rich hormone codes under the scene. And rich hormone codes were actually used in deep space mission. So it was implemented in Voyager 1 and 2. And these 2 were launched in 1977 to take the images of Jupiter, Saturn. And I just read a little bit about them, and it turns out that these Voyagers, those robotics probes, they are still flying in the space nowadays. So it's from 1977, and then all the scientific equipment is still working. But 2020 is a year where they start to run out of batteries, and they have to be deactivated one by one. But just let's think how long they last, from just 40 years ago, more than 40 years ago. So the focus of this talk is actually in the usage of rich hormone codes in major distributed storage systems. And I have listed a few large system here from companies like Google or Backblaze or Baidu or Yahoo and Facebook. And they all use some kind of read-someone codes for their storage systems. Noticeably, I'm going to talk about this read-someone code 9.6. I'm going to explain what 9.6 are. And the read-someone code 14.10, which is used by Facebook in their F4 system. So I will mention these two quite a bit later. So first, let me explain how the data is stored in a data center. So this is the look of a typical data center cluster. So each cluster consists of several racks. So each of these columns is a rack, and each rack consists of a number of servers. And your data is stored in the server, so normally it's stored across different racks, so that if you lose, if one rack is down, then you can still have other racks to back it up. And let's imagine this is your rack. Okay, so you have a couple of racks here, and each rack has a couple of servers. So if you are going to store your movie or your data or your image there, you're not going to store your data in just one server, one rack. We are going to store it in different servers across different racks, so that there is a level of redundancy there. So if, let's say, this rack is down for whatever reason, then you still have the other two to back up. Or actually, in this case, two racks can be down and your data is still available. So, so this is called the triple replication. So you just create 3 copies of your data and then distribute them to 3 different servers on 3 different racks. So this is simple and fast, but it incurs a very high storage overhead, 200%, as you can see. So the question is there a smarter way to store A and B redundantly? Turns out there is, and we can store A here, B there, and in this server we'll store A plus B, while this one you will store A plus 2B. So it's another a different linear combinations of A and B. So it turns out that and B can be recovered from any 2 selections of this 4. So that means you allow any 2 servers to fail and your data is still available. For example, if you lose the 2 in the middle, then from the first one, A and A plus 2B, you can just solve a linear system and recover A and B. So these are actually called erasure codes in the literature, and read-someone codes can be seen as the most popular erasure codes in practice. Invented by Reed and Solomon back in 1960, and the construction is based on a very neat polynomial constructions. So you have, so I'm going to present the construction of read-someone codes very quickly. So we have 2 parameters here, n and k. So k is actually the dimension of the data vector m. So let's say this is your movie, and the movie has k parts. In this case, we are talking about the symbol. So we are talking about the finite few elements. So m1, m2, and mk are element in some field, and the finite few in this case. It can be a byte for each. And then from this data, you are going to form a polynomial, univariate polynomials of degree at most k minus 1 using mi, your data, as the coefficients. And then for this code, you have to select a set A of n evaluation points. Okay, so n is the second parameter of the code. And these are distinct points in the field, alpha 1 up to alpha n. So you transform this data into a code word. So this is a redundant form of your data by evaluating this polynomial at these endpoints, alpha 1 up to alpha n. And so each of this, and let's say we denote C1 as f of alpha 1. The first we call it code word symbol. C2 as f of alpha 2 as a second code word symbol. And the last code word symbol Cn is f of alpha n. So each of these code word symbol is stored at one server. And in this case, you are transforming k code word symbol, k symbols, k data symbols into n code word symbols. So the redundancy level there is n minus k. We also refer to this as the number of parities. So suppose n minus k servers are down and k servers are still active. And notice that f is a polynomial of degree at most k minus 1. And therefore, it can be recovered uniquely using any k evaluations. So if k servers are active, you can retrieve these k evaluations of f, and then to recover f itself. And then because the data m1 up to mk are coefficients of f, we can recover this coefficient as well. So these are the data. So basically, we have introduced n minus k redundancy or parities. And that can help us to tolerate n minus k erasures. And this is the best possible according to something called the so-called Singleton bound. So this is the best. So Ericsson code is the best in terms of the storage overhead, given a redundancy level, given the number of erasures that it can tolerate. So what's wrong with Ritz-Solomon code then? I need to keep track of the time. So what's wrong with Ritz-Solomon code? So let's look at the Facebook code used in the system F4. So it is Ritz-Solomon code 1410 means n is 14 and k is 10. And the number of parities or redundancy level is 14 minus 10, which is 4. So this code actually protects data from machine or rack failures. And 14 data chunks are placed in 14 different racks to avoid rack failures. So these are the 14 servers across 14 different racks that hold the code word symbols of this code. You have 10 data nodes and then 4 parity nodes. So it has been observed that, so this is the observation from a Facebook cluster, that every day there are a number of node failures in the clusters. For example, you see here, this is a daily records of the number of server failure. So you can see the average number or median number here can be like 20, more than 20, and it can reach up to 100 servers failures per day. And moreover, most of these failures are single failures, just a single machine fails across the 14.1. And so they actually have like 98% single failures. So what happened when one server is down? So how does the Ritz-Solomon code repair itself? So if the Ritz-Solomon code loses this server, then basically it loses 256 megabyte here. And then the way it used to recover is to use a spare server as a replacement node. And then that replacement node will contact for 10 other nodes. It contact 10 other available nodes and try to download all the data. So 10 times 256 megabyte gives you 2.56 gigabyte. And so basically it downloads all the data there and repair the data, repair the whole movie, for example, and then to after that recover whatever is stored here before. So basically you have to download 10x more data to repair just a single piece of data, which is very high bandwidth. So actually, in one of those clusters of Facebook, the traffic used for repairing Ritz-Solomon coded data takes about 10 to 20% of the whole traffic, which is really huge amount. So we talk about the default repair scheme. or the naive repair schemes that the current systems are using. So I should make sure that I define the repair bandwidth here. So the repair bandwidth basically measures the amount of data that the replacement node has to download from all the helper nodes in order to recover the lost content. Okay, just how many bits or how many megabytes it has to download. So suppose one node is down, let's say node 1, then this repair scheme would just need to recover C1 as the first code word symbol, and it will contact K helper nodes. For example, node number 2, 3, and K plus 1. So I'm using node and server interchangeably. So the key thing here is that it's downloading all data from K nodes. For example, they're downloading the other K code word symbols C2, C3 up to CK plus 1. And then after downloading this, it will have a K equation, K unknown linear system, and then it can solve it. And then to recover M1 up to MK, all the data, and then reconstruct the polynomial fx as before, like the encoding, and then it repairs C1 by evaluating f at alpha 1. So basically, the naive repair of Ritz-Solomon code actually requires the bandwidth, the repair bandwidth, the same as the data size, which is pretty bad. So the question here is, can we improve the repair performance of Ritz-Solomon codes? So it's used everywhere. We really need to improve them. Okay, so the first work in this direction is by Shanmugam, Papaliopoulos, Dimakis, and Kare back in the 2014. So their key observations are as follows. So these come from the literature of regenerating codes, but I'm not touching that topic today. So they treat each code word symbol CJ not as a whole symbol, but as a vector of L subsymbols over FQ. So now the field that we are using is FQ to the L. Okay, so the field, finite field of Q to the L elements, and each element in that field can be treated as a vector of L subsymbols over FQ. And in practice, normally L is 8 and FQ is just a binary field. So that means each field element CJ here, each code word symbol CJ is just a byte, and a byte consists of 8 bits. So each of the subsymbol is just a bit. So when we pass CJ, the helper node J doesn't send the whole CJ. Let's say it doesn't send the whole byte, but just send a few bits of that byte. For example, it sends CJ1, the first bit, and CJ2 plus CJ3, which is the sum of the second and the third bit of that byte. Okay, so it doesn't send the whole byte, it just sends a few bits. And it contacts n-1 helper nodes, so all remaining nodes. So one node is down, we have n-1 left. So we contact all helper nodes, but download less data from each. And as a result, the total amount that we download is less than the naive scheme. And then they go on to demonstrate their techniques. They develop a few techniques there in the paper and applied their techniques on a different number of codes, including the Facebook code, Ritz-Solomon code 1410. And then they show that they can reduce the repair bandwidth by 20%. Okay, so the second work, which is a breakthrough in this area, is by Guruswamy and Wouters, published at STOT in 2016. So they still rely on the observation that each code word symbol can be treated as a vector of L subsymbols. So we split the code word symbol into a number of subsymbols, but they use the concept of field trace. So let's say alpha is an element of the finite field, FQ to the L, and you can use the trace of alpha. And trace of alpha is computed as the sum of alpha to the Q to the I, and I runs from 0 to L-1. And turns out that it is well known that the trace turns out to be linear. It's a linear map. And the trace value is always in FQ. And more importantly, any linear combinations of, let's say, the bits of the code word symbol is some trace. It's a trace of gamma times Cj for some finite few element gamma. And when we pair C1, so we are talking about linear repair, meaning we are sending some linear combination of the bits of C1. Then the helper node Cj actually sends out the traces of Cj, and not sending the whole Cj, just a few traces. So the remaining question is, the first question is, what traces to be sent from the helper nodes? And then how to recover, the second question is how to recover the lost symbol C1 from those traces from the helper nodes. So one more piece of this, the whole picture here is the trace repair technique. Yep.
Yeah, so this is Prasad. I have one question in the previous slide.
Absolutely, yep. Let me come back to the previous.
So this fourth point, like any linear combination of Cj1 to Cjl is a trace of this thing. So that's pretty easy to show, is it?
Yep, it's pretty easy to show. Yep.
Okay. Yep. Thank you.
Yeah, you can count the number of. So it's known that the trace of gamma times is a linear mapping, and then you can count the number of linear mappings like that, and then it is exactly the, I think it's Q to the L, and it is exactly the number of linear combinations.
Okay, thank you.
Yep, but it's pretty easy. Yep. So the second piece of the picture is the trace repair technique. So how would you repair the C1? So actually C1 can be repaired from L traces. Trace of beta I times C1, where beta I run, so I run from 1 to L. If the beta I forms an FQ basis of the finite field FQL. And so that means if you want to recover, so it makes sense because C1, let's say C1 is a byte consisting of 8 bits, then each of these trace is 1 bit. And then if you know, 8 bits of information about C1, then you can recover C1. So those bits are just linear combinations of the bits of C1, and more or less like you are solving a linear system here, more or less for the bits of C1 as unknown. And the fact here is that if you know, once you know the traces of beta I times C1, you can write C1 as this sum. And what is a beta I star here? So beta I star here forms the trace dual basis of this basis. So basically it says that if you know a number of traces of C1, and those traces are independent in a sense, then you can recover it easily using a formula. It's existing formula, quite easy. So this one is also easy to prove as well, like a few sentences, a few lines. Okay, so this is the whole picture about trace repair framework. Okay, we are still missing something, but let's try to capture the main parts of the trace repair framework. So you have encoded your data into a code word C1, C2 up to Cn, so n code word symbols. So now suppose your C1 is lost, so the server is lost, and the replacement server comes in and trying to recover C1. And because we are using the trace repair technique, in order to repair C1, we're trying to generate some traces of C1. So trace of beta 1 times C1, trace of beta 2 times C1, or to trace of beta L times C1, as long as beta 1, beta 2, beta L form a basis of the finite field. Then from these traces, you can recover C1 using this formula. So this piece is done. So it's easy, okay? So how to recover C1 from their traces is easy. And on this side, so these are the helper nodes. So those store all other code word symbols and they play the role of helper nodes. They are sending over their traces. So this traces, for example, this one star C2 is going to send over a few traces of C2, which are the linear combinations of bits of C2. Okay, so these are a few bits, and these are sending a few bits. All of them are sending a few bits to the replacement node here to help with the recovery of C1. So there are two unknown questions. There are two unknown things here. The first unknown thing is how to generate the repair traces. So how do you know what to send here? Okay, so that's the first question. And then suppose you know what to send here, you still need to find a way to transform all these helper traces. I call it the repair traces, to generate these target traces here that C1 can use, the replacement node can use to recover C1. Okay, so we don't know how the helper node will generate the repair traces here. We don't know how to combine these repair traces to generate the target trace. I'm calling this the target traces that C1 can use. So there's still missing thing here. And it turns out that we can use the repair equations. And those repair equations can be constructed using the dual code words from the dual code. And that's how we are going in, what we are going into now. I don't seem to see the chat box, so let me see if there's any chat. Is there any questions? So if you have any questions, let me know.
Not right now, Hoang. So I don't think there are any chat text right now.
Okay, thanks. It's half an hour, so probably it's a lot of content right now. So if you have any questions, then just shoot in the chat box, and I try to address all the questions. So this is the whole trace repair framework. Still missing this one. Okay, so I'm going to talk about this part. So how to combine all the traces. Okay. So how to create the repair equation to combine the traces. So let's say C is the NK code over, I'm talking about the F2, oops, I think it should be F2L here. So I'm assuming that we are doing over binary. So it should be L here instead of T. I think I use the old version. Richardson code, dimension K. And so the dual of this code, so complement, orthogonal complement space of that code. So I didn't define it, but it's a basic from algebra. So I can assume that a basic knowledge in algebra and also some knowledge in coding theory here. I couldn't cover all of them. So let's say this C-perp is the dual of this code, and so it is of the same length n, but the dimension is n minus k. So it's a dual code. So if C with the vector here, so this is a code word in C, and G, another vector here, is a dual code word in the dual code, then the definition is that if you take the inner product of these two vectors, then you have the 0. So if you multiply them coordinate-wise, pairwise, coordinate-wise, you sum all of them up, then it should be 0. And because you want to repair C1, right? So you want to recover this one, you put this one on the right-hand side. You put this one on one side, and then on the other side, you have the minus of G2 times C2 minus G3 times C3, and so on and so forth. So we want to recover this thing from this, okay? So the critical step here is to apply the trace function here. And the trace function actually maps an element in F2L to F2, maps to a bit. And so if I apply the trace to both sides of this equation, then I got trace of G1 times C1 equal to minus trace of G2 times C2 minus trace of G3 times 3, and so on and so forth. And that happens, I can put all the trace out like this because of the linearity of trace. And so if you look at the left-hand side here, it's actually the target trace of C1. So one of the target trace of C1 that we want to recover. And on the right-hand side here, they are the repair traces coming from the helper nodes. So we have successfully established a relation between target trace of the C1 and the helper traces from the helper nodes. But we are, as we said earlier, we are going to need L traces L target traces for C1 in order to recover it. So we need L of these equations. So in order to get L equations, we need L dual code words. Okay? So that's what we are going to have here. So we are, instead of G, we are using L code word, dual code word G1 up to GL. And I'm just going to write down L equations corresponding to this L dual code words. So this corresponds to the first dual code word. This is second dual code word. And we have L equations here. And each equations, so the helper nodes are going to send this to the replacement node. And the replacement node using these equations to recover the traces of C1. And then from these traces of C1, it will recover C1. And as before, when we talk about the trace repair, we need these elements to form a basis of the field. So that's why we need this element to have full rank. So rank is L, so that we can recover C1. So this must be a basis of FQL. So that is a condition for the L dual code word to serve as a repair scheme. So let's take an example here. I'm talking about binary code. L is 3, so the coding field is F8. The length is 8, and so it's 86 Riemann codes over the F8. So psi here is the primitive element of the field. So F8 is just 0 and all the powers of that primitive element. And so I need to use L or 3 dual code words G1, G2, G3. I just write all of them down here, and I will explain how to get to this dual code word later. But for this moment, you're assuming that we know how to choose these 3 dual code words. And using these 3 dual code words, you can just build the 3 repair equations. And it just goes like this. So 1 here go to here, so 1 times C1, 0 will multiply C2, psi cube will multiply with C3, and so on and so forth. So it's direct corresponds between the coordinates of the components of the G and the coefficients here. Okay, so I saw some message saying you can't see the share slides. So can you guys see my share slides?
So Hoang, I'm able to see it.
So do you see the side and the side square with red fonts?
Yes.
Okay.
Yeah, there is no problem at our end. Yeah.
You guys can still see it. So probably there's some internet issue with Sing's side, so she cannot see it.
Could be.
Yeah, could be. Okay, so I'll continue, but I think you can try to log in again to see if the problem is resolved. Okay, so we have these three repair equations. Okay, and then the important thing here is to make this into a repair equations is the side and the side squared here should be a basis of the field, and it is obviously the basis. So I have intentionally chosen to be the basis of the field F8. Okay.
So question.
Yep.
So this G2 and G3 vectors, they have been chosen as some scalar multiple of G1 itself, right? So G2 could have been psi into G1.
Yes. Okay. Yeah, you could have chosen to be the multiples of G1. Yeah.
Okay.
Yeah, it could have, but the bandwidth might not be that good. So you could easily do it. So you can multiply the G1 with psi and then multiply itself with psi squared, and then you get yourself a repair scheme.
Okay, but then this particular choice will affect the bandwidth. That's what you're saying.
Yeah, so it's easy to make a repair scheme. Just choosing this column to be independent elements or rank 3. but it's hard to come up with a good bandwidth. So we'll show the bandwidth later. Yep. So I think that's a good question. So it's easy to create the repair scheme. Okay, so how do we repair this? Suppose this is the code word C, and the first symbol C1 is lost. You don't know what it is. So the other are available at the servers. So 7 other servers, they're still available. So now I'm going to use these repair equations and trying to recover the traces of C1 and then trying to recover C1. So now I'm going to substitute C2 up to C8 in this. Okay, so you know C2 is 1, C3 is size squared, and so on. So I'm going to substitute all of this J in the right-hand side of this. Okay, and then I compute it, and then I got the first trace of C1 is 1, the second trace of C1 is 0, the trace of size squared times C1 is 0. Okay, and I'm going to use this is a basis, right? So the one size squared is a basis, and I can easily figure out the dual basis of this is 1 size squared and psi, and so on. And therefore, if I use the formula I have before with the dual basis, then C1 is just the trace, the first trace times the beta 1 star, the second trace times the beta 2 star, and the third trace multiplied with the beta 3 star. And using this formula, which is easy to prove, as I said earlier, I can recover C1 to be 1. So that's how we recover this the loss symbol C1 using the trace repair. So there are two parts to a repair scheme. One is it a repair scheme or not? So that one is easy to deal with. But the second part is whether it has a low repair bandwidth. So what's the repair bandwidth in this case? So you can see here that the left-hand side is what the replacement node is trying to collect. And all of these traces on the right-hand side have to be supplied by the helper node. So the helper nodes have to send all of these traces. So the second node will send, these 3 traces. The third will send the 3 traces, and those, so on and so forth. So for example, the node 4 here storing C4, node 4 need to send this trace of psi to 6 times C4, psi to the 2 times C4, and 1 trace of 1 times C4. And the question here is, would that count as 3 bits or not? So if this one is going to send 3 bits, that is going to be not good, because 3 bits means we are going to send the whole C4. So C4 just consists of 3 bits. You are sending 3 bits, that means you are sending the whole C4. We are not saving anything. So it turns out that we don't have to send, C4 doesn't have to send all these 3, and it actually has to send only 2 bits. You just send the first 2 traces, the red one. And the reason is because of the linearity of trace. The third trace, trace of 1 times C4, turns out to be the sum of the previous 2 traces. And that because the psi to 6 plus psi to the 2 is 1. So it turns out that these 2 numbers add up to 1. And that's why we don't need to send this redundant trace, which is to send 2 traces. And so that holds for every other helper node. And so all helper nodes just need to send 2 traces or 2 bits to recover C1. So they don't have to send the whole 3 bits for each code word symbol, just send 2 bits. And that should be enough to for the replacement node to create all these equations, the right-hand side, and then recover the left-hand side, and then recover the C1. So the repair bandwidth in this case is 7 times 2 bits, which is 14. So 7 nodes are helping. Each node send 2 bits, and that add up to 14 bits.
So okay, so you're going to say how you guarantee that such dual code words exist, right? I mean, you have to pick the dual code words carefully, I guess.
Yep, so that is the key problem of this repair framework. So yep, you got to the right, to the heart of it. So before I go into it, I'll continue with the bandwidth. So in general, how to compute the bandwidth of the repair scheme. So suppose we are using L dual code words, G1 up to GL, to create this L equations, repair equations. So how to compute, first, is this qualify as repair scheme? So to qualify as a repair scheme, this column here corresponding to C1 should form a basis, or it should have a full rank L. And then to figure out the bandwidth, like how many bits each node has to send, you look at the rank of these elements. And let's say this rank is B2. The rank of the third column is B3, and so on. The last column is Bn. And so the total repair bandwidth turns out to be the sum of this Bi, sum of these ranks. So it's very easy to figure out the bandwidth. So if we look at the example before, we are using 3E repair equations. And if you look at all of these columns, they all have rank 2. And that's why you only need to send 2 traces. And the third trace will be the sum or whatever linear combinations of the first 2 traces, just because of this rank. They all equal to 2, and that ends up with the 14 bits of repair bandwidth. So I've just described how the repair bandwidth is calculated from the repair scheme. So the key question here is, so just as Lalita just asked, is how to find the set of the L magical dual code words GI that satisfy the 2 conditions. So one is the repair condition, which means that the first column here, so let's say in this case, I use J star as the loss symbol. So CJ star is a loss symbol instead of C1 to make it general. So the rank of the columns corresponding to J star should be L. So it's full rank there. It should form a basis there. The column should form a basis at the position where we want to recover. And the second condition is the low bandwidth, where we compute the ranks of all other columns. We sum all of the ranks up, then that sum should be minimized. So full rank at one column and a low rank at other column. So basically those are the 2 conditions that you need to address. And the question is how to find those L dual code words that satisfy both of these conditions. Okay, so there have been quite a number of words. I haven't included all of those here, all in here, but just a note here that all this work can be classified into 3 regimes for the parameters n and l. So there are works that study the case when l is in the order of log n. Then there are also some work study the case when L is constant, like 8. So the middle column here correspond to the codes that industries are using. Yeah, I'm going to talk about it for quite a bit, quite interesting here. And then the last column here means the L is exponential in N and K. Okay, so L is very large. So we refer to L as a sub-packetization of the code. So L is super large here. So I'm going to one of these regimes one by one.
So if I may, maybe it's a slightly away question, but I was curious. I thought this one is somewhat related to the minimum storage regenerating codes, right? Which requires, sub-packetization very high. So in the regime of, let's say, L constant or L log n, will the bandwidth be suboptimal here?
Yep. So you are right. So absolutely right. So these columns here correspond to the MSR code in regenerating codes. For those area, then the bandwidth is definitely far away from the cut set bound. So it's not achieving the cut set bound for these regimes. And And so, but we have another bound. So it's impossible to achieve the cut-set bound with this small subpacketization L. But we try to optimize, we still try to optimize it. It won't achieve the cut-set bound, but it will achieve some bound, other bounds.
Okay, thank you.
Yeah. Okay, so the first regime is when L is roughly log n. Okay, so before we ask how to find the dual code words, so how to find dual code word to use to generate the repair equations. And for Rich-Solomon codes, then each dual code word actually corresponds to a polynomial. So the dual of Rich-Solomon code is again a Rich-Solomon code. So their code word correspond to polynomials. So it turns out that we are looking for polynomials of nice properties. And so the first work in this, the first optimality result here, we can find those polynomials using the trace or subspace polynomials. So this was introduced by Guruswamy Wouters using trace polynomials, and later we extended to use subspace polynomials and can cover a broader range of parameters. And so in this direction, then we consider a code with n equal to q to the L. So that means the length is the same as the size of the field. And R also has a nice form. So this is the number of parities or redundancy level. It is q to the m. And m is smaller equal to L. So notice here that R has a very nice form. It's a power of q. So the dual code in this case is also a Rich-Solomon code generated by polynomials of degree at most R minus 1, which is qm minus 1. So the goal is to repair Cj star, which is f evaluated at alpha star with low bandwidth. And the question here is how to select a set of L polynomials of degree at most q to the m minus 1 and satisfying the repair condition and the low bandwidth condition that we have it here. So again, we're looking for a set of good polynomials of degree at most qm minus 1. So the method that we can use here is we need to define a subspace polynomial. So let's look at an m-dimensional subspace U of FQL over FQ. So this U will have q to the m elements. So we define a polynomial LU of x is the product of x minus u for all u in capital U. So basically the root set of this polynomial is u itself. And this is a linearized polynomials. So I haven't defined it, but it is a linear mapping as we know in the literature. So it's easy to see that because u has q to the m elements, the degree of this polynomial is q to the m. And then the kernel of this mapping is just u itself. So the dimension of the kernel is m. So next we are going to choose a basis, beta I. And then we are ready to generate the polynomials that we are looking for. So the polynomial, the ith polynomial, we define by this LU, and inside, instead of x, we replace it by beta I times x minus alpha star. So alpha star is the place where we want to recover, and divided by x minus alpha star. So we can notice that because LU has degree q to the m, because we divide it by x minus alpha star, the whole thing has degree q to the m minus 1. Okay, so it just has the right degree that we need for the dual code word polynomials. And so after we have these polynomials done, set up, then we generate the code word, the dual code word gi with the vector here, with the arrow here. By evaluating these polynomials at the evaluation points alpha 1, alpha 2, up to alpha n. So that's how we generate the dual code word DI, by generate the polynomials from the subspace polynomial. So just select, so to summarize, you select a subspace of dimension m, you create a polynomial LU, it's called the subspace polynomial, and then you're going to generate the polynomial GI using the LU, and then you evaluate this polynomial at this n evaluation points and get the dual code words. And then it's kind of easy to check. Okay, I'm not going to check here, but believe me, it's easy to check that if you look at the column J star where we want to recover, it is exactly the basis beta I. So that satisfies the repair condition that we have here. So the rank of the column J star is L, which is equivalent to saying that this is a basis. And then the more important thing here is if you look at the column J, then it is LU of something divided by this constant. And the LU of something here should all belong to the image of this mapping LU. And why is that important? It belongs to the image. And this image, we know that it has dimension L minus M because the kernel U has dimension M. So we have the nullity theorem. So the image should have dimension L minus M. And all of these values lies in this image. And that's why the rank of this column should be at most L minus M. So we want rank to be low, right? So we want this rank to be low. And so the bandwidth is the number of helpers, which is n minus 1 times the maximum number of bits that's going to be sent. So it's L minus M. And then this turns out to be optimal. So we have a lower bound. This turns out to be optimal when for this parameter n equal to q to the L and r equal to q to the M. So that is kind of the first optimality result that people have in this direction, in this regime. And I have time. I have to go faster. So just look at the, I think I provide an example here, but probably I'm not going into this. So I'm just trying to explain that how do I create the polynomials in the example before. In this case, I'm just choosing the subspace U to be just 0 and 1, so it's one dimensional. And in this case, I'm considering the number of parities R is 2 to the 1, so M equals 1. That's why I'm choosing U to have dimension 1. And then, so the subspace polynomial is just x minus 0 and x minus 1 and x squared minus x. And then we can plug in the formula. We get this is the polynomials corresponding to the dual code word. And so we have 3 polynomials here, and we can evaluate this polynomial at these 8 points, and then to get the dual code word. And then you compute rank of the columns. They're all 2 magically, but it is due to the selection of the subspace polynomial. They're all 2, and so the repair bandwidth is just 7 times 2, which is 14. And it is optimal in this case.
Hoang?
Yep.
Yeah, so quick question. So how does this optimal bandwidth compare to the naive bandwidth?
Yes, so if you look at this code here, so if you have, so in this case, n is 8 and r is 2, that means k is 6. And so the naive bandwidth is 3k times L. So it's 6 times 3 is 18. So 18 bits for the naive. So 18 bit is still greater than this number of bits that we have. So most of it, so I think all of the time it should be lower. So the bandwidth here should be lower than k times L, the naive.
Right. And in general, is there an expression on what is the optimal bandwidth?
Yeah, we do have it. Yes. So I think the optimal bandwidth is here. So n minus 1 times L minus M. And if you plug in the n is q to the L, then this is certainly smaller than the k times L if you plug in the numbers.
Okay, thank you.
So yeah, so in general, it's smaller.
Hey Wang, this probably a basic question. So the dual of a Reed-Solomon code is in general a generalized Reed-Solomon code, right?
Yep, that's right. Yep. So in general, it is a generalized Reed-Solomon code. Yeah.
Okay, but then the scheme that you are describing, that will hold that as well.
Yep, it holds that as well. So generalized Reed-Solomon codes just have some extra column multiplication. So every column will have an extra gamma j. And actually the gamma j doesn't affect the rank, because if you multiply the whole column with gamma j, the rank remains the same. And so it doesn't affect the bandwidth.
Okay, thank you.
Yep. So, but that is an important question. So actually we wrote it in the paper, explain why we can ignore the generalized Reed-Solomon codes. So again, here oh yeah, please.
Sorry, this is related to Lakshmi's question. So does the original code actually matter, or is it all with the properties as a dual code that you get what this bandwidth is?
Yeah, the dual code, yeah, so it matters more the dual code, but it is like equivalence, right? So once you determine the dual code, then you have a unique original codes. So you're working more with the dual code. Yeah, that's right. I think that's a good observation.
Okay.
Yep.
Thank you.
Hong, one question. Has this scheme been extended number of helper nodes strictly less than n-1?
Yep. So that's a good question. So generally, if you reduce, so in the regenerating code, you use the number d. So as a number of helper nodes. So instead of n-1, you can go down like n-2, n-3. So we can generalize the repair scheme to that case. But we may not get the optimal. So I think we don't have the low bound for that case. For this regime. So for this regime, the answer is we can, but we don't know if we can get optimal or not if we reduce the number of helper nodes down below n-1. But for another regime, so I go back to the last regime, then actually the authors consider general D, the number of helpers general, and do get reaching the cassette bound. Yep.
Okay. Thank you.
Yep, so that's a good question of the number of helpers. I can't ignore it, but until the end, but you brought it up, so that's good. So so basically the open question left for this regime is we need to find optimal bandwidth repair schemes when R is not the same as QM, and when N is smaller than Q to the L. Okay, so I didn't say it, but basically we have obtained optimal code only for very special case of N equal to Q to the L and R equal to Q to the M. So all nice parameters, but all about other parameters, we don't know what's happening. So a lot of open questions here. I'm done with the regime 1. So now I'm moving to the regime 2, where we consider industry codes. They're all in this regime, where L is 8. So all of them are using a byte for a code word symbol and 8 bits. Okay, so what I just said, Q is 2, L is 8, and each code word symbol CJ just has 8 bits. It's the byte. And the number of parities normally lies in the range between 2 and 4. So the level of redundancy here is from 2 to 4. That means it can recover 2 to 4 failures or erasures. And then, so the dual code in this case is an generalized Reed-Solomon code. I didn't define it, but if you know what it is, then it is more or less similar to Reed-Solomon code. It's some column multiplier, as I just mentioned with Lakshmi. But it's not important though. So the dual code is generated by polynomials of degree at most R-1. So we are talking about linear polynomials or quadratic or cubic polynomials at most. So we are looking for the set of polynomials to generate a good repair scheme. So n is normally small. So the one in the table that I show is the largest one is 20. So these are considered to be short codes. So L is 8, R is 2 to 4, and L is smaller than or equal to 20. So there are a couple of noticeable aspects of this code. So they mainly over GF 256. So the field with 256 elements, or represented by a byte or 8-bit. Okay, so think that when we did research on the codes that industry used, so it turns out that there are 5 different constructions of Rich-Solomon codes, and one of them is invalid. So we'll see in the next slide. So they may use different sets of evaluation points A. Okay, so before we have an evaluation point set A, but because n is small, we can choose different set of A. So the immediate question is, which one is the best, or they're all the same or not? So we'll discuss those questions next. So the first, so this is from textbook, right? So this is the standard polynomial evaluation that I described in this talk, comes from Ritz and Solomon themselves, using the polynomial evaluations. And I haven't explained what is the generator matrix, but it is just a way to generate the code, and they use it. They use a Van der Waals matrix. So basically, these constructions is equivalent to using a generator matrix, which is a Van der Waals matrix built up on these endpoints. So that's also the second textbook construction is using generating polynomials, and they actually equivalent to saying what is a parity check matrix. So the parity check matrix in this case is just a Van der Waals matrix of, let's say, 1 psi up to psi n minus 1, where psi is the primitive element. And it turns out that Facebook, the code Facebook used, it actually used this construction. So if you read through the papers in the literature, most actually mention this code. Okay, so they always try to improve this one. Oh, yeah. Although I think probably Facebook no longer uses this code. The next one, this is also very popular in practice. It is a systematic one, systematic part plus the Cauchy. So the generator matrix goes like this. So the G is consists of identity matrix and a Cauchy matrix, and the Cauchy matrix is just defined as this way. So it is just the ij element is just 1 divided by xi, should be minus, but plus is also fine, xi plus yj, where xi and yj are distinct elements from the field. So you put an identity matrix, you put the Cauchy matrix. So actually Intel and HDFS, they are using these constructions. And there's also another construction used by Backblaze. So they use this double Van der Waals matrix. This was in the work of Lacan and Films. And the generator matrix is like this. So it has the identity part to make sure that the code is systematic. And then the parity part is V1 inverse times V2, where V1 and V2 are both Van der Waals matrices. Yeah, so this one is used by Backblaze. And there's another interesting one. So they use the same as the systematic plus Cauchy, but they use systematic plus Van der Waals. So they use IK. So in the generator matrix, they have the identity part and then the Van der Waals one. And clearly, this is a curious case because this is not Rich-Solomon code. And this is not even an MDS code in general. Okay. So I don't know why they used it, but probably it is still an MDS code. So I haven't said about MDS code, but it is like equally good as Rich-Solomon, probably because it is still an MDS code for some small parameters, but it doesn't hold in general for sure. We know it. We know that it's okay. So we have 5 different constructions. So are they equivalent? So the first 2 textbook constructions, they actually equivalent. We know them in theory. This these constructions that are used by Intel, HDFS, and backplace, they're also equivalent to the polynomial construction that we described in this talk. So by the result by Roth and Sarosi, and clearly this one is not. Okay, so this is, I would say, it is an invalid one, and the remaining 4 are valid. So it's a good thing that we have all the equivalents, and basically saying that all valid construction can be reduced to polynomial constructions that we are relying on.
Hong, just one quick question about the invalid thing. Is there any care choice which will make it valid, or for?
I don't think so. So you may, yeah, I think there's no systematic way to select the V, the Van der Moon matrix, to make it into
Matrix,
the
for
generator
example,
matrix like this.
Yeah.
Yeah,
Okay.
Cauchy matrix always work, but Van der Moon is, there's no guarantee. There's no
Yeah.
guarantee. I think it's also pointed out in this paper that, you know, people have used this one without knowing that this one actually is not going to work in general.
Okay. So Hoang, maybe a very minor remark. I think at some point we have come across one example where such a matrix is actually in use. But maybe it's a very peculiar case, but I've seen one example.
Yep. So definitely, so they are using it, and those examples are valid. So when they use the V, they're indeed an MDS code. So it satisfies good properties. But I'm just saying they won't work in general, but they work in those special cases that they use. Yep.
So one more.
Yep, Professor. Yeah.
So this choice of these various matrices, are they essentially motivated by how quickly you want to recover if there are failures?
Yep. So I think the choices. Okay. So we'll go into the choices later. But the first thing is the identity part here. You just want the code to be systematic, and yeah. So basically that's a key point. And the remaining part, I think we'll going to discuss in the next part. Yeah, but that's an important point. So we go to look into a few codes that we have. For example, the first example is the rhizome code 96 by Intel and HDFS. So this one was used by Google, but we know we cannot find any information about their actual implementation. So actually, probably they are, so they're not open. So we don't know. But HDFS is probably the open version of that Google file system. So probably it's more or less the same. So the rhizome code 96, the set of evaluation point is this. Okay. So basically, we just go with 0, 1, psi, 1 plus psi, psi square, 1 plus psi square, psi plus psi square. So basically, it corresponds to the binary representation of the first 9 integers from 0 to 8. And why is that? We'll look at why is that. And then the second example with the Facebook code is that they use this straightforward evaluation point. So all the powers of psi from 0 to 13, where psi is a primitive element of the field. And so we kind of realize that, okay, so when we talk about rhizome code 96 or rhizome code 1410, there are actually many of them depending on how we select the evaluation point. So that makes it more challenging and also more interesting. So the first question that you may ask here is, why did they choose the above sets of evaluation points? So I just, at least at this moment, we just found out that it's just convenient for programming. You just write the for loops. For example, for the RS96, because they are using the integer representations, they just run the for loops running 0 to 8, and that's it. They generate the binary representation. They convert it into back into the finite few elements, and that's it. I didn't find any particular reason why they use it other than convenience. Okay. Also, I think for Facebook code, it's also kind of convenient. You can choose a different set. So the second question is, do all the sets of evaluation points achieve equal repair bandwidths? Okay, so we can choose different set of evaluation points. So do all of them give the same bandwidth or not? And the answer actually no. Interestingly, no. So the evidence that we found is the following. So we look at the Shanmugam's, so this is the first work on repairing Ritz-Solomon code. They applied their technique on the Ritz-Solomon code of length 5, dimension 3 over F16. And they proved that, okay, the optimal repair bandwidth is 10 bits. Okay, so that is the lowest. So we did the exhaustive search using the trace repair framework that I described in previous slides. So out of this 16 choose 5 choices for A, only 48 sets A have the bandwidth 10 bits. So actually it is the worst. Okay, 10 bits is the worst. And the rest actually achieve 8 or 9 bits. So most of this A would give you 8 or 9 bits as the repair bandwidth, while the one chosen in the previous work actually give you 10 bits. Okay, so different set of evaluation points actually give different bandwidths. It can get more tricky. So which one is the best? So we are not able to answer that question yet, but at least we can answer some easier questions. We say, okay, so if all of them are not achieving the same repair bandwidth, then which set of evaluation points do achieve the same repair bandwidth? So for this, we can say something. We know that the sets that are translations or dilatations of each other achieve the same repair bandwidth. So by that, it means that the code evaluation point set A or A plus some gamma, so it's a translations of A, or it is a dilatation of A, so gamma times A. They all have the same repair bandwidth. So this can be proved quite easily, like a few sentences, using you just transform the polynomials, and that's it. Okay, so the question 4 is how to find repair schemes. Okay, so how to find repair schemes that have low bandwidth. So I think at this moment you can see that I kind of gave up on the questions of which evaluation point set is the best. We haven't been able to answer that one yet. But we are going with the next question is how to find repair schemes that have low bandwidths. If you fix the evaluation point set, how to find the best repair scheme. So the brute force approach is goes like this. You just go for an exhaustive search for all sets of 8 polynomials of degree at most r-1. So you go through all of this. So there are 8 polynomials. You check the repair conditions, you check the bandwidth, and then find out which one is the lowest bandwidth. But it is quite intractable, so it's it is very high. It is very high complexity. So you can't go with this over F256, even over F16, and R is 2 or 3. It is already very tricky. So there are a couple of tricks to reduce the search space. We can consider special polynomials. So this is a nice thing about polynomials. We can consider polynomials of certain degrees that have certain number of roots, and the roots lies in certain set. Okay, so we have all different ways to just look at a special set of polynomials instead of looking at all polynomials. There's also a lifting technique that has been used in a couple of other works. You can transfer, so basically 256 is too big, and the search space is huge. So what if you work on the F16 and find out a repair scheme over F16, and then you lift it up to 256? So there's a technique called the lifting technique. Very straightforward. You can just find a repair scheme over F16 and then multiply with certain basis and then get it into F256. And it turns out the result quite good. So let's look at the applications of some of this technique. So for example, if we look at the Facebook code, then the current best is come from I'll work with Iwan Dusmar and myself a few years ago. So we get the improvement up to like 32.5%. So it's a reduction in bandwidth compared to the naive repair schemes. So we use a special polynomials technique there. And then if we look at the lifting technique, so the lifting technique has the limitation that you have to consider the set of evaluation points within the subfield F16. Okay, so if you ignore the Facebook code, but you use a different read-someone code 1410 with a different A, then you can reduce it further by a reduction of 35% to 52 bits. And this one was done by Wei Chi Li, Wang Juying, and Hamid Jafarkhani. I think they just published not a long time ago. They use a lifting technique and subspace polynomials that we discussed earlier. So if we look at the 9.6, then if we look at the original code of Intel and HDFS, then we can reduce it by 29%. We use a special polynomials and exhaustive search, okay, basically. But if we use the lifting technique, we reduce, we consider a different A, okay, over F16. Then we can reduce further by 32%. So it's pretty much like the case in the Facebook code. And of course, we use a lifting technique and special polynomials. And there's some of the reduction too. So I think what we are doing is we're trying to make up a table, to work on give a table, so that what's the best improvement that people got so far on this codes. We can actually do it for all shortcodes. Okay. So a lot of open question here: how to choose the best evaluation set A. Then if you fix A, how to search for the low bandwidth repair scheme efficiently, and develop a tighter lower bound. There's no good lower bound right now. How good is the lifting technique? We saw that it's quite good, but how good is it? Optimal? We don't know. How good is it when we use special polynomials? We don't know. We are working on it, but the partial answer is it's enough to use polynomials of degree exactly R-1, so we don't have to care about low degree polynomial. So that saves us something. So a lot of open question here.
Hoang, there is one question from the audience. For L equals log n and constant regime, how much read happens versus bandwidth? I think the question is, would trace computation involve access of all the L symbols?
Oh yeah, you're talking about the access, right? The access. Yep. Okay, so I think I'll go to the access a bit later. So the access is normally larger than the bandwidth. And the quick answer is, we proved that for the subspace repair scheme that I described earlier, then the access is pretty bad. So access is like equal to the file size. So access is kind of trivial. So that is one of those strange results, that you can save the bandwidth, but you have to sacrifice access. You have to access the whole file, more or less.
Okay, thank you.
Yeah. Thanks for the question. So I think I'll go into the third regime and then quickly finish with a few notes on a few related problems. So this regime, we consider a very large subpacketization. So like in the regenerating code, where the L is exponential in n, actually it's n to the n. Okay, so it's more than exponential. So this is the work from Tamo, Ye, and Bark, published with Fox 17. So they basically fix the Q, they fix the length, they fix the parameter of the code. But the special technique that they use is they select a special set of evaluation points and show that for this particular Rich-Solomon code, there exists a repair scheme achieving the cut set bound. And this is a big deal. This is important because the cut set bound is actually the smallest bandwidth among all erasure code and not just the read-someone codes. So basically, by this result, they show that they can construct the read-someone codes, achieving the best bandwidth among all possible erasure codes. So that is very powerful result. And that works for any number of helpers. So as one of the questions coming from the audience. So that works for any number of helpers, D. So it is as good as the MSR. Okay. So the way they choose it is to select the special finite few elements that have some prime degree over FQ. And those would be the distinct primes, and then the GCD of each of those degree, and D minus K plus 1 must be 1. Okay, so the downside of this is it requires as a subfactorization is this, and which is estimated to be n to the n, which is very large subfactorization. And if you look at the example of the minimal read-someone code 4.2, then it's required that L is 2,310, and so the field size is huge. So it is highly impractical. So to summarize on this direction, so actually this is a very nice set of papers they have, and deserve probably a few talks, not just one talk. So if you fix all the code parameters and allow this L to be sufficiently large, then we can construct the read-someone code and a repair scheme, achieving the cut set bound. Okay, so the price to pay for that is to have extremely large subfactorization. So, so other problems that I haven't had time to mention is to repair multiple erasures. There are quite a few number of works, but most questions are open in most regimes. So I listed a few works here. And also the problem of access. So people usually use access, but I use the repair IO costs. It's the number of bits that you need to read. The helper node need to read. There are quite a number of, just a few initial works on this direction. So basically, let me explain. So this is the last bit of the talk. So what's the difference between the bandwidth and the IO? So suppose you have two helper nodes like this, and this is the replacement node. And this one stores 2 bits, A and B, and sends over A XOR B. This one is going to send D. So the bandwidth in this case is just 2 bits. So they are transmitting 2 bits, A plus B and D. Yeah, so 2 bits. Bandwidth 2 bits, but the IO is 3 bits. And the reason is that these helper nodes are reading 2 bits. This one is reading 1 bit. So 2 plus 1 is 3. So you are reading more than what you're sending. And in this case, the IO is greater than bandwidth. Yep, so there are a few works here, but most questions are actually open. Okay, so to summarize, then I have provided the basics of the trace repair framework to read-someone code. So after this, you can just jump right into the heart of the problems. And then I also discussed the application of this framework to codes of theoretical interest in 2 regimes, and then those used by the industry as well, and lots of open problems for future research, including finding the optimal bandwidth. For this code, which when n is great, is different from Q to the L, I is different from Q to the M, and optimal bandwidth for its own code used in industry. So no one knows what are the optimal bandwidth for this code used in industry. And the trade-off between repair bandwidth and the repair IO. So one of our papers discussed this, but a very initial result. And then also repair multiple erasures. Okay, so with that, I'll just finish the talk, and thank you for staying through all the talk, 1.5 hours. Thanks a lot.
Thank you, Hoang. Thank you very much for giving us such a friendly introduction to this topic. I guess we already have some questions in the chat box. So if you have time, you can answer them.
Okay, so I think I can see the chat box, right? Let's see. Okay, so I saw the question on access. Will the access be larger than KL? It may be larger than KL. But for those games that we have seen so far, it is at most K times L. So that's the question from Mina. So there's another question asks whether something can be said on blind identification of Rich-Solomon codes and its variants, how it is different from other type of erasure codes. Yeah, I'm not quite sure about the blind identification of Rich-Solomon codes, what it is. Different from other type of erasure codes. So it is just one special kind of erasure code. So that's, yeah, I'm not quite sure how to answer the question. So if you can clarify, that would be great. I think the question from Mina, I think.
Hi, Som. If you are listening, can you maybe type in a response to Hoang so that we can understand your question better?
Type the questions, you mean?
Yeah.
Let me try to do it.
No, so Hoang, I was talking to Som, so the person who posted the question. We tried to connect his audio, but we could not.
What
He
did
can clarify his question. Maybe he can type in a clarification so that we can understand his question.
Oh, yeah. Yeah, so he said that blind identification of Rich-Solomon code, I'm not quite sure what it means. So do you guys have any other questions? Again, I'm waiting for this, but any other questions?
So questions from my side, Hong. One is that the current Reed-Solomon codes, let's say, which achieve the cut set bound, have I guess they have more subpacketization than the MSR codes, right?
I think it's larger. Yeah.
So that was one thing. Second is, what is your take on? So there is another line of work which does this, epsilon MSR kind of codes. Means I guess similar work exists in Reed-Solomon also, where you kind of slightly back off from the optimal bandwidth, and then but still you gain a lot on subpacketization.
I can't remember exactly if the work by Guru Swami and a co-author was right on that epsilon capacity. So it's like almost reached the capacity, but within the epsilon factor.
Yeah.
I can't remember. It is MSR or Reed-Solomon codes.
So the original work, I guess, was MSR. Maybe it was extended to Reed-Solomon codes.
Yeah, so that was by Guru Swami and someone else, right?
Okay, yeah. So, I mean, I was wondering if those kind of codes are, because they have much lower subpacketization.
Yeah, I think so. I just can't remember if they already did it for Reed-Solomon codes or not. I couldn't remember. Probably this for MDS, general MSR, and not the Reed-Solomon codes. Yeah. Okay. So I think I think they haven't done it, and that seems to be a nice work to do. Nice question to ask for Reed-Solomon codes. So you said you have two questions.
Yeah, I already asked you. Yeah.
Okay.
Hoang, that's a follow-up from
Okay, so I saw here. Okay, this is some. Okay, blind identification suppose data with other FEC and data along with some code is given as different files. How one can identify? Suppose data with other forward error correcting code, forward error codes, and data along with Reed-Solomon code is given as different files. How one can identify, like how one can identify if it is a Reed-Solomon code or some other codes in action, right? I think. So probably that is clear. Like when you do a protocol, then you kind of know which codes you are using. So there's probably not an issue of distinguish between read summon codes and other codes.
So Hoang,
Yeah, I'm not entirely sure if that is what is asked.
So Hoang, I think the point is that the person who is looking at this data doesn't know what the encoding scheme is.
Yeah. So you look at the data and you don't know the encoding scheme. And that case is I think it is a question that I've never thought of before. Because normally when we work with the system, we kind of know what kind of code we are dealing with. Like if your friend sending you something, then you kind of know what you guys have to agree beforehand what code we are using. If we are just receiving something and we don't know what code it is, then I don't think we can decode. So we can only decode if we know what mechanism that has been used. So I kind of think that we can't really identify, we can't really tell if it is this code or that code. Yep, so actually I don't know. So I don't know how to do it.
So Hoang, I have a question.
Yep.
Yeah, so is there any interest in thinking about, let's say for given values of n, k and l, right? So is there any interest in thinking about what would be the code which has the maximum possible bandwidth?
The maximum possible bandwidth, you mean minimum or maximum?
Maximum. So the motivation for this question is, so something related to something like secret sharing, right? So just like Reed-Solomon codes are, variant of that is used in secret sharing, right?
Mm-hmm.
And you don't want people who can up to a certain number of evaluations to be able to decode the data.
Okay, so I think maximum is easy because if you just consider a constant, so let's say the first your code word is a constant, let's say O1, and then the second your code word is O psi, and then the next is O psi squared, and so on and so forth. So every column would have full rank L. So that would give you the worst case, like the maximum possible bandwidth. So I think that would come trivially if you just use a constant dual code word.
Okay.
Yeah. So yeah, I don't know if that will help in the cryptography case, the secret sharing case. Yep. But probably we can modify the question a little bit and not in just straightforward way. Then it may give some interesting questions and solutions there.
Right. So for instance, it could be like this IO thing which you talked. Right? So
Okay, maybe that. Yeah, maybe you should. Yeah, maybe you should think about the IO. Like there's some other constraints, and not a complete freedom to choose the dual code words. So there might be some other constraints, and then you want to maximize the bandwidth. So that may work.
Right. So under related to this, is this modified sort of repair process, does it have any applications in some other problems? Right. So for instance, private information retrieval.
Yeah. So if you think of let's say you store the information, the code word symbols at different servers, and then you want to retrieve a certain piece of information without them knowing, and you want to retrieve as little bit as possible, I think probably there's some work on that already. Yeah, I think definitely there's a direct link between these two, saying we want to minimize the number of bits that you are downloading from those servers to retrieve your information without letting them know what you're downloading. Yep, but I couldn't recall immediately what the result would look like, or if someone has done it or not. But I think definitely that is an interesting question. Yeah.
Right. Thank you.
Yep.
I have one question. This is related to the subspace polynomials. I'm also aware of, let's say, linearized polynomials, right? So, yeah, this subspace polynomial setting, are you losing anything, or instead of a generalized, instead of a general linearized polynomial for your repair, what's a subspace polynomial? Does it come for free?
Yeah, it comes for free. Yeah, so we don't lose anything. And we need the subspace polynomials instead of linearized polynomial because of the we need to make sure that the kernel of the mapping has the right dimension and have the right degree as well. Like yeah, so there's a restriction on the degree of the polynomials and the size of the kernel. And if you go with general linearized polynomials, those conditions are not satisfied. If you use subspace polynomial, you don't lose anything.
Okay.
Yeah, at first we just said it is a linearized polynomial, but turns out subspace polynomial is a more accurate way to call it. Even think of, like, say, is there a more general version of linearized polynomial? But probably there is none.
Yeah, I mean, does subspace polynomial, it need not have to divide certain x power something minus x? Is that an additional condition? I don't know.
I think so. I think that's the additional condition is you have to divide some x. Yeah.
Okay.
Yeah, something like that. Yeah.
Sure.
So not all linearized polynomial will satisfy that.
Okay.